So this is problem number 4, dealing with frames. And what we have here is what we call a propped cantilever beam. A cantilever would just have a fixed support by itself, but here it's propped in the sense that it's supported also by rollers over here. Now usually that's an indeterminate type of structure where you have a propped cantilever. In this case we've made it determinate by adding internal hinges, and we'll see why that's the case. So here we have a fixed support at A, an internal hinge or internal pin at B, roller at C, hinge at D, and a roller at E. The loads that are applied, we've got 2 forces, a 9 kilonewton and a 10 kilonewton force, as well as a couple moment that's applied to the beam at C. So it's asking us to find the support reactions at A, C, and E. And we can't do it based off of, let's say, a global free body diagram here. So if I were just to write on what the support reactions look like, we've got a vertical component at A, AY. We've got a horizontal component, AX. We've got some bending moment, M sub A. Those are our reactions at A because it's a fixed support. At C, I would have some vertical reaction CY, and at E, I'd have some vertical reaction EY. So if I were to do a free body diagram and run equilibrium for the global model for the entire structure here, I would have 1, 2, 3, 4, 5 unknowns, but I'd only have 3 equations of equilibrium. So it looks like it's indeterminate on the surface because of the global free body diagram, but with many frames that you're going to see and many machines that you're going to see, all that we have to do here is divide and conquer. So we know that the internal hinges can transfer some force. We don't know the direction of it, so we usually represent that by some unknown force in the Y, some unknown force in the X. But if we break this up into 3 separate free body diagrams, then we can divide and conquer and kind of work our way down from one free body diagram where we have enough equilibrium equations down to the other one where it seems like we don't. Okay, so here, this is essentially the method of sections. What we're going to do is we're going to make a section cut that goes right through the pins, and then we'll draw a free body diagram of section AB, a free body diagram of section BD, and a free body diagram of section DE. This should be point E. All right, that section cut is going right through the pin, and so we'll replace everything on either side of that by just the forces transmitted by that pin. Okay, so let's just draw the free body diagram of all of these out at once, and then we'll figure out where we should start. And so here we've got section AB, and we've got a horizontal beam. And I might as well just draw that out for each of these so I can plan out my room. We've got B, D. Again, all of these are just horizontal beams, so it's relatively straightforward to do the outline. And then we've got section DE, also just a horizontal beam. Okay, so that's just the outline of the member. We need to add things like support reactions, external loads, things like that. And just a note for all of these, I will use the exact same coordinate system, X positive to the right, Y positive up, and counterclockwise rotations or moments are positive as well. Okay, so for member AB, on the left-hand side we've got our fixed support, which means that we have our 3 unknown reactions. And so AX, AY, and then some couple moment reaction MA. On the right-hand side, I have, you could think of them as reactions as well too, but I have this internal hinge transferring some unknown forces. And so I can assume any direction that I want. Here I'm just going to assume that in the y direction, B is reacting up. In the x direction, I'm going to assume that B is acting positive to the right. Again, it doesn't matter which way you assume, the signs will work themselves out at the end. So if you get a negative value, you know that you just assumed the wrong direction. Okay, but that's not a complete free body diagram yet. We have two more things we need to add. So one is this 9 kilonewton external load. And so that is right here, 9 kilonewtons. And the other thing that we're missing is simply the geometry, where this 9 kilonewtons is acting, where point B is relative to point A. And the distances here are a uniform 1.5 meters for everything. Okay, so this complete free body diagram for section AB is helpful, but it's not going to be where we can start to kind of unravel all of these reactions and internal forces, and we'll talk about why. So here, we've got a complete free body diagram. Our section cut was, everything to the right of our section cut was replaced by the forces transferring across that section cut at that pin. I should probably show the pin here as well too. But if I were to run equilibrium here, I've got three equations I can run. Some of the forces in the x, some of the forces in the y, some of the moments about any point. But I have 5 unknowns at this point: ax, ma, ay, bx, and by. So I can't start there, but it is important to have it set up because I can come back to it later once I've solved for bx and by. Okay, so let's go ahead and complete the free body diagram for section BD now. So here at BD, I've got a roller support in the middle, which is going to give me the reaction CY. I should probably label these points as well too. So I guess this last one wasn't exactly complete, but here it's point A, point B. Here we've got point B, we've got point C, and at the end over here at the other pin we've got point D. Okay, so there's our support reaction. That's the only support reaction that we have, but we also have an internal type support, this internal hinge. And so at B and D at either end, we need to transfer some vertical and some horizontal force. And at this point, it's still unknown, but we need to draw it consistent with the other free body diagram. So here I've already drawn bx and by, my assumed directions of these. And at B in this free body diagram, it needs to be consistent. And again, this is one of Newton's physical laws, equal and opposite reactions. So here, bx is pointed to the right on this free body diagram. So here it has to be pointed to the left. And that's still going to be bx, it's just opposite in direction. Likewise, in terms of by, I just have to draw it in the opposite direction. Okay, so as a result, I still need to also show my reactions here. So here at D, some vertical component and some horizontal component. I'm going to assume the same that I did over here, going up at D, going right at D for dy and dx. All right, I'm almost done here, but I need to draw my externally applied loads, and I need to draw my geometry as well. So externally applied load, we have a couple moment that's applied right here at point C. It's a clockwise couple moment, and it has a magnitude of 9 kilonewton meters. And the last thing here that's going to be important would be the geometry. So 1.5 meters, 1.5 meters. All right, but again, if we're counting up or looking at whether or not each of these are determinant, here we find that we've got 1, 2, 3, 4, 5 unknowns, but just like before, we only have 3 equations of equilibrium. So we can't start there either. So the last option the last section that we have is section DE, and this has the internal hinge on the left-hand side, and it's got a roller at E. So the roller at E can only provide a perpendicular reaction. So just like we drew on our global free body diagram, we've got a vertical reaction there. And I also need to transfer over these internal hinge forces to the hinge here at D, and so I'll draw them equal and opposite to what I did on this intermediate free body diagram. Okay, and we've also got an external loading here. It is 10 kilonewtons at mid-span. I've got to label my points and provide the geometry. This is point D, this is point E, and everything here is spaced out in even 1.5 meters. Okay, so this is a much more doable free body diagram because we only have 3 unknowns and we'll have our 3 equations of equilibrium. So this is where we want to start. We need to start with section DE because this is determinant, and once we've solved for dx and dy here, that's the same dx and dy over there. So here 2 of my 5 unknowns will become known. I'll only have 3 unknowns and I'll have 3 equations of equilibrium. I'll be able to solve for everything, and that will include bx and by. I'll transfer those over here. My 5 unknowns becomes 3, and I have enough to solve for all the support reactions. So it doesn't hurt to just always start from the left frame and go to the right. You'll just find which one allows you to start first, and you can kind of work your way backwards. So here, a couple equations of equilibrium to solve for everything. The sum of the forces in the x is equal to 0. And the only horizontal force that I have here is this dx. And so I get that dx is equal to 0. All right, that means that dx here is equal to 0. Dx over here will also be equal to 0. So that's great. All right, if I sum the moments about point D equal to 0, I will get 10 kilonewtons causing a clockwise moment about D. So that's minus 10 kilonewtons times a moment arm of 1.5 meters. Then I've got EY causing a counterclockwise rotation about D. So that's a plus EY, and its moment arm is, 3 meters. So here, just one unknown EY. I've got my loading, my known information, and my distances. So I get the EY is just simply equal to 5 kilonewtons. All right, so that's one of our questions here. And I'm going to summarize the solution over here as well, too. I'll provide a summary. We know that EY is equal to 5 kilonewtons going up. All right, so we've already solved for 1/3 of what it's asking us for, but we need more than just this from the free body diagram to be able to then transition down to the next. And so at this point, I've got EY. This is just 5 kilonewtons. But I need dy now. And so I can either sum the forces vertically, or I could sum the moments about either this intermediate point or point E if I wanted to. I'm just going to, it doesn't really matter. Let me just go ahead and sum the forces in the y equal to 0. And so here I get minus dy minus 10 kilonewtons plus 5 kilonewtons, which is EY. And so in this case, I get that dy has to be equal to negative 5 kilonewtons for this to be in equilibrium. Okay, so dy is a negative value. That just means that I guessed the wrong direction for dy. And so I could, if I wanted to over here, I could flip this upside down and give it a positive magnitude, but I'm just going to leave it in the same direction but give it a negative magnitude. So this is negative 5 kilonewtons. That's the same thing as flipping it upside down and giving it a positive magnitude. Okay, so we're done with this free body diagram over here for DE. Now we've gotten everything out of it that we can, and I've transitioned, I've copied over the forces that we calculated here to the pin at D. Okay, so now I want to solve for not only the unknown support reaction here at C, but also the internal hinge forces at B. Okay, so a couple different ways that we can do that. I could sum, let's say, the moments about point B. So if I sum the moments about point B equal to 0, I'm going to get no contribution from Bx, no contribution from By, because they're both coincident to B. Here my 10 kilonewton meters is going clockwise, so that'll be a minus 10 kilonewton meters. That's just the couple moment that's applied at C. In addition, the vertical reaction at C is causing a counterclockwise rotation about B, so I'll get plus Cy, and its moment arm is 1.5 feet. Or 1.5 meters, I'm sorry. And then here, so as I have dy shown, it's causing a counterclockwise rotation. So if d was positive, this would be positive, but the magnitude is a negative 5 kilonewtons. And so even though the assumed direction would cause a positive moment, here, because I have a negative magnitude, the signs are going to work themselves out. Its moment arm is 3 meters. Okay, so in this case, I get that Cy is equal to 16.7 kilonewtons. There's only one unknown, which is just Cy. So I get Cy equals 16.7 kilonewtons. I can summarize that over here. Cy equals 16.7 kilonewtons going vertically. Okay, so we've got Cy, but we're not done with this free body diagram yet because we still care about By and Bx. And so Bx is easy. I just sum the forces in the x equal to 0. I get negative Bx plus 0, plus dx, which is just equal to 0. So Bx equals 0, and so Bx over here is going to be equal to 0. Not a big deal. Now to solve for By, I've got a couple different options. If I sum the forces in the y direction equal to 0, I'm going to get minus By plus Cy, which is 16.7 kilonewtons, right? And then plus dy, that has a magnitude of negative 5 kilonewtons. So plus negative 5 kilonewtons. All right, so here By just ends up by itself on one side, then we get 16.7 minus 5. I get that By equals 11.7 kilonewtons. So here we guess the correct direction of By. I assumed that it was going down, and the signs worked out where I got a positive value for By, so I did guess the correct direction here, which is great. So here, By is 11.7 kilonewtons, and now I can work on the last free body diagram. So now it's a determinant system. I only have 3 unknowns here and 3 equations of equilibrium because I solve for the internal hinge forces. So the first is going to be solving for Ax. If I sum the forces in the x direction equal to 0, I simply get Ax plus 0 has to equal 0. So in other words, Ax equals 0. that's one of my answers. I get AX, that's a support reaction, is equal to 0 kilonewtons. Likewise, if I want to get AY, I'm just going to sum the forces in the y direction equal to 0, and I will get AY going up, which is positive, 9 kilonewtons going down, which is negative, and then 11.7 kilonewtons going up, which is plus 11.7 kilonewtons. And so I get that AY is equal to 2.7 kilonewtons. That's another answer. That's my vertical force reaction at A. AY equals 2.7 kilonewtons, and that's going up, so I'll denote the direction right here. All right, and the final unknown support reaction is the couple moment at A. And so here, if I sum the moments about A equal to 0, a lot of students have a hard time with this. So in the nomenclature, the variable names are somewhat unfortunate. So here, this sigma MA means that we're summing all of the moments about A. That's different than the MA right here. This MA is the reaction moment at A. It's part of what causes a moment about A, but it's not the only thing that we consider down here. And so here, part of the moments about A will be due to this couple moment, that's the reaction, but part of all of the moments about A will also be due to this force and this force over here. All right, so just keep in mind that the sum of the moments about A includes this couple moment, and it includes these forces times their distances. So AY and AX don't cause any moment about A because they're coincident, but this couple moment sure does, and here we have it shown counterclockwise, and so it's going to be a positive whatever this reaction is. That's the unknown that we're trying to solve for. The 9 kilonewtons causes a clockwise moment at a distance of 1.5 meters, so that's minus 9 kilonewtons times a moment arm of 1.5 meters. And then finally, this BY reaction, the 11.7 kilonewtons, is causing a counterclockwise reaction, which is plus 11.7 kilonewtons times its moment arm, which is 3 meters. One unknown, just the moment reaction at A, and I get the moment reaction at A is equal to negative 21.5 kilonewton meters. That just means that I guessed the wrong direction of MA, which is totally fine. So we know that in reality, because it's negative, that means it is going to be rotating clockwise, in a clockwise direction. So in here, the moment about A is equal to 21.5 kilonewton meters in the clockwise direction.